In this tutorial, we're going to show how a Kasiski attack is used to crack a Vigenere cipher. There are 5 general steps to a Kasiski attack. We look for repeated strings, assuming that repeated strings occur because the same set of plain text letters lined up with the same letters in the keyword. Once we do that, we look at the distances between them. The length of the keyword should divide most of those distances. So if we can find a divisor that works for most of them, that's likely to be the keyword length. Once we have that, we subdivide the ciphertext by the keyword length. Each subdivision should be monoalphabetically encrypted, so we can do frequency analysis on those and figure out, all right, E has probably been enciphered with one of the high frequency letters in each subdivision. So we look at the high frequency letters, assuming that E gets mapped to one of those, we look for the needed shift to make that encryption. This gives us a grid of potential shifts. So when we look at that grid, we look at the letters involved and see if we can recover a keyword. The following commands in the MCP will be of use for us. DFT, which is short for digraph frequency table, that's going to show us all of the different possible digraphs. If we have trouble finding repeated strings, this can be useful. Find string, once you have the beginnings of a string, maybe you can find a longer one using this. The Kasiski command will compute the distances between repetitions for you so you don't have to go through and count. Subdivide graph, once we have the length of the keyword, or the potential length of the keyword, subdivide will we'll subdivide it and compute the letter frequencies on each individual subdivision. And then keyword grid, that's going to, once we give it the high frequency symbols, figure out the shifts for us, and hopefully we can spot what the keyword is. All right, so I already have the MCP loaded and evaluated. This ciphertext was given to me by a colleague who encrypted it back in his office, and I don't know anything about it other than I know it's been encrypted with a Vigenere. So we're all in this together, and let's see if I can figure this out. And I will show you all the steps along the way. Okay, so step 1, I need to see if I can find repetitions in the ciphertext. All right, I want to look for strings of at least 2 characters. The longer the better, and see if they repeat with any sort of regularity. All right, sometimes this is just a matter of looking through and seeing if you can spot them just by hand or by eye. For example, ZDI occurs here and it occurs here. All right, don't know if there are others, hopefully there are, but let's start making a list just to keep track. Hold on a sec, I hit the wrong thing. Okay, I had to pause there for a moment because I made a mistake when I was editing. All right, so let's have a look and see what repeated strings we can find. All right, as I mentioned, ZDI I spotted occurred a couple of times. As I look through, all right. Did I see? No, I don't think I did. All right. Oh, look, there's a nice one. NZWWR and NZWWR. Okay, so we'll use that. NZWWR. All right. Now, I could continue trying to do this by eye, but I'm going to use some of the commands just to show you how they work. All right, so this command will give us the digraph frequency table. Okay, so we look at all first letters on the rows and all second letters on the columns. So what I want to do is look through here and see if I can spot some high values. There's one there, KL. Okay, and there's another one, RV. Okay, so I'm going to put those into my list. All right, but now what I'm going to do, I'll use my find string command, and I will feed it sort of a seed string. All right, and when it goes through, it notices, it looks at all possible extensions of this string by other letters of the alphabet. All right, so you never find KLA, B, C, or D, but there are 3 repetitions of KLE. There are 4 repetitions of KLI. And there's 1 repetition of KLR. Okay, so what I'm going to do now, I'm going to go a little further. Find string. And since there were 4 repetitions of KLI, I'm going to see if I can get it longer. All right. And no, not really. There's only one time these things, so they never repeat. In other words, they only appear once. All right, so we'll amend this to KLI, though, because there are 4 repetitions there. All right, so now let's go through and find distances. Okay, so what I will now do, I'm just going to copy these again. All right, so I'm going to look at the Kasiski distance inside Vig1 of all repetitions of ZDI. All right, apparently only repeats once, and so the distance between those repetitions is 280 characters. All right, I will do the same for this one. ZWR. Oops, forgot to put a message. One. Okay, occurs a couple of times. All right, we get a distance of 15 and a distance of 20. All right, so now let's do the same thing with KLI. And then the same thing with RV. Okay, so, well, let's have a look. So I need numbers that divide most of 280, 15, 20, 75, 25, 365, and then this long string here. All right, well, these two are pretty restrictive, okay? The only number that divides both of them is 5. So assuming that this isn't a fluke, and it's hard to believe a 5-letter string is a fluke. So that tells me 5 is a good choice. 5 divides 280, 5 divides all of those. It divides 1, 2, 3, 4, 5 of these and doesn't divide 21 and 284. All right, well, that's okay. Because, again, we're assuming that we get these repetitions because the plain text and the keyword line up again. But we could also get some flukes. The fact that there are 2 repetitions, especially on a short string like RV, makes me think that's probably okay. I'm going to guess that my keyword length is 5. Now, it's a guess. I think it's a good guess with all of these values, but it is a guess. All right. All right, now that we've got the keyword length, we're going to subdivide the graph, or sorry, subdivide the text. I'm going to use the subdivide graph command, and then a potential keyword length of 5. Okay, so let's have a look. We'll go through character by character. K has a very high frequency compared to the others. That's almost certainly what E gets mapped to. But again, when you're doing this, the subdivisions aren't actual English words. So the letter frequencies can get a little corrupted. All right. But we'll just make a note And I'm going to write this on a pad of paper in front of me because I don't want to keep scrolling back and forth for the moment. All right, so the first letter, we assume that E gets encrypted as one of K, Z, or maybe X. All right, again, a really high spike on the second letter with V, and then it looks like F, K, and Z are all about the same. So I'm going to do all of those. All right, so here we get two things almost exactly alike. Don't know which one of those it is. All right, and S and W aren't too far behind, so I'll take those as well. All right, bunch of high frequencies here. I'm going to go with EISX, and I'm not going to put the W in. I think if it doesn't work, I'll come back for that, but I think with these three spikes, one of those is going to be the E. All right. Oh, and that's great. All right. So for the fifth letter, H, L, Q, R. Okay. So now we use command keyword grid. All right. I'm going to give it a list of letters. I give it the letters that I think E got encrypted as. So the first letter I thought E was probably one of K, Z, or X. For the second one, it was V, F, K, and Z. For the third, it was EIS, W. For the fourth, it was EIS, X. The fact that three of those four letters are the same in both instances is interesting. And then lastly, HLQR. All right, so what keyword grid will do is basically it's the equivalent of taking a recta and looking at, all right, what shift do I need to encrypt E as K? And then E as Z, and then E as X. Okay, so we get this. In order for E to be sent to K, Z, and X, it would have to be sent by either G, V, or T, respectively. Then likewise for VFKZ, it would have to be sent by R, B, G, and V, EISW, AEOS, etc. All right, now to find my keyword, I have to take one letter from each column. Okay, and I have to take them in order. I can't reuse a column, I can't skip a column. All right, they don't all have to be in the same row. All right, so I see one word immediately. So the word I see is greed. G-R-E-E-D. There may be others. It's highly unlikely to start. If it was going to start with a T, we'd have to follow with R. I'm not really seeing anything else. I'm going to see what happens with greed and see if that does the trick. I did one keyword greed. Yep, that was it. Okay, so Marley is dead to begin with. And as you keep looking, it's clearly it is clearly English text, and it looks like Scrooge. All right, so my colleague, it looks like, has encrypted A Christmas Carol. All right, so there it is in all its glory. It's got a few steps, but thankfully Mathematica does all the scut work for us, and usually you can crack them pretty quickly.